Hi, everybody, and welcome to this session where we're going to talk about breakthroughs in machine learning. I'm Laurence Moroney. I'm a developer advocate at Google, working on TensorFlow with the Google Brain team. We're here today to talk about the revolution that's going on in machine learning and how that revolution is transformative. Now, I come from a software development background. Any software developers here? Given that it's I/O, sure. And this transformation, this revolution is, particularly from a developer's perspective, is really, really cool because it's giving us a whole new set of tools that we can use to build scenarios and to build solutions for problems that may have been too complex to even consider prior to this. It's also leading to massive advances in our understanding of things like the universe around us. It's opening up new fields in art, and it's impacting and revolutionizing things such as healthcare and so many more things. So should we take a look at some of these? So first of all, astronomy. At school, I studied physics. I wasn't a comp-sci person, so I'm a physics and an astronomy geek. And it wasn't that long ago when we learned how to discover how new planets around other stars in our galaxy. And the way that we discovered it was that sometimes we'd observe like a little wobble in the star. And that meant that there was a very large planet, like Jupiter size or even bigger, orbiting that star very closely and causing a wobble because of the gravitational attraction. But of course, the kind of planets we want to find are the small rocky ones like Earth or Mars, where there's a chance of finding life on these planets. And finding those and discovering those was very, very difficult to do because small ones close to the star you just wouldn't see. But with research that's been going on in the Kepler mission, they've actually recently discovered this planet called Kepler 90I by sifting through data and building models for using machine learning and using TensorFlow. And Kepler 90I is actually much closer to its host star than Earth is, so that its orbit is only 14 days instead of our 365 and a quarter and a bit. And not only that, which I find really cool, that they didn't just find this as a single planet around that star. They've actually mapped and modeled the entire solar system of 8 planets that are there. So these are some of the advances. To me, I find it's just a wonderful time to be alive because technology is enabling us to discover these great new things. And even closer to home, we've also discovered that looking at scans of the human eye, as you would have seen in the keynote, with machine learning trained models on this, we've been able to discover things such as blood pressure predictions or being able to assess a person's risk of a heart attack or a stroke. Now, just imagine if this screening can be done on a small mobile phone. Now, how profound is the effect going to be? Suddenly, the whole world is going to be able to access easy, rapid, affordable, and non-invasive screening for things such as heart diseases. It'll be saving many lives, but it'll also be improving the quality of many, many more lives. Now, these are just a few of the breakthroughs and advances that have been made because of TensorFlow. And TensorFlow, we've been working hard with the community, with all of you, to make this a machine learning platform for everybody. So today, we want to share a few of the new advances that have been working on this. So including, we'll be looking at robots. And Benson's going to come out in a few moments to show us robots that learn and some of the work that they've been doing to improve how robots learn. And then Debbie is going to be from NERSC. She's going to be showing us cosmology advancements, and including showing how building a simulation of the entire universe will help us understand the nature of the unknowns in our universe, like dark matter and dark energy. But first of all, I would love to welcome from the Magenta team, we have Doug, who's a principal scientist. Doug.
Thanks, Laurence.
Hey, thanks, Doug.
Thank you very much. All right. Day 3, we're getting there. Hi everybody, I'm Doug. I am a research scientist at Google working on a project called Magenta. And so before we talk about modeling the entire known universe, or we talk about robots, I want to talk to you a little bit about music and art and how to use machine learning potentially for expressive purposes. So I want to talk first about a drawing project called SketchRNN, where we trained a neural network to do something as important as draw the pig that you see on the right there. And I want to use this as an example to actually highlight a few, I think, important machine learning concepts that we're finding to be crucial for using machine learning in the context of art and music. So let's dive in. This is going to get a little technical, but hopefully it'll be fun for you all. What we're going to do is try to learn to draw not by generating pixels, but actually by generating pen strokes. And I think this is a very interesting representation to use because it's very close to what we do when we draw. So specifically, we're going to take the data from the very popular quick draw game, playing Pictionary against a machine learning algorithm. That was captured as delta x, delta y movements of the pen. We also know when the pen is put down on the page and when the pen is lifted up. Okay? And we're going to treat that as our training domain. One thing I would notice is that, or observe, is that we didn't necessarily need a lot of this data. What's nice about the data is that it fits the creative process. It's closer to drawing, I argue, than pixels are to drawing. It's actually modeling the movement of the pen. Now, what we're going to do with these drawings is we're going to push them through something called an autoencoder. What you're seeing on the left, the encoder network's job is to take those strokes of that cat and encode them in some way so that they can be stored as a latent vector, the yellow box in the middle. The job of the decoder is to decode that latent vector back into a generated sketch. And the very important point, in fact, the only point that you really need to take away from this talk, is that that latent vector is worth everything to us. First, it's smaller in size than the encoded or decoded drawing, so it can't memorize everything. And because it can't memorize, we actually get some nice effects. For example, you might notice, if you look carefully, that the cat on the left, which is actual data, and has been pushed through the trained model and decoded, is not the same as the cat on the right. The cat on the left has 5 whiskers, but the model regenerated the sketch with 6 whiskers. Why? Because that's what it usually sees. 6 whiskers is general, it's normal to the model, whereas 5 whiskers is hard for the model to make sense of. So this idea of having a tight, low-dimensional representation, this latent vector, that's been trained on lots of data, the goal is that this model might learn to find some of the generalities in a drawing, learn general strategies for creating something. So here's an example of starting each of the 4 corners with a drawing done by a human, David, the first author, and those are encoded in the corners, and now we just move linearly around the space, not the space of the strokes, but the space of the latent vector. And if you look closely, what I think you'll see is that the movements and the changes from these faces, say from left to right, are actually quite smooth. The model has dreamt up all of those faces in the middle, yet to my eye, they really do kind of fill the space of possible drawings. Finally, as I pointed out with the cat whiskers, these models generalize, not memorize. It's not that interesting to memorize a drawing. It's much more interesting to learn general strategies for drawing. And so we see that with the 5 to 6 whiskered cat. I think more interestingly, and I think it's also suggestive, we also see this with doing something like taking a model that's only seen pigs and giving it a picture of a truck. And what's that model going to do? It's going to find a pig truck, because that's all it knows about, right? And if that seems silly, which I grant it is, in your own mind, think about how hard it would be, at least for me, if someone says, draw a truck that looks like a pig. It's actually kind of hard to make that transformation, and these models do it. Finally, by the way, I get paid to do this. I just want to point that out as an aside. So it's kind of nice. I said that last year. It's still true. OK, so these latent space analogies, another example of what's happening in these latent spaces. Obviously, if you add and subtract pen strokes, you're not going to get far with making something that's recognizable. But if you have a look at these latent space analogies, we take the latent vector for a cat head, and we add a pig body, and we subtract the pig head. And of course, it stands to reason that you should get a cat body. And we can do the same thing in reverse. And this is real data. This actually works. And the reason I mention it is it shows that these latent space models are learning some of the geometric relations between the forms that people draw. I'm going to switch gears now and move from drawing to music and talk a little bit about a model called NSynth, which is a neural network synthesizer that takes audio and learns to generalize in the space of music. You may have seen from the beginning of I/O with bathing that this has been put into a hardware unit called NSynth Super. How many people have heard of NSynth Super? How many people want an NSynth Super? Good. OK, well, that's possible, as you know. OK, so I want to, for those of you that didn't see the opening, I have a short version of the making of the NSynth Super. I'd like to roll that now to give you guys a better idea of what this model's up to. Let's roll it.
That's like wild to me. Here's a flute. Here's a snare. Guess in the middle, this is what it sounds like.
Now it does feel like we're turning a corner of what could be new possibilities. It could generate a sound that might inspire us.
The fun part is like, even though you think you know what you're doing, there's some weird interaction happening that can give you something totally unexpected.
Why? Wait, why did that happen that way?
Okay, so what you see here, by the way, the last person with the long hair was Jesse Engel, who was the main scientist on the Ensign project. This grid that you're seeing, this square where you can move around the space, is exactly the same idea as we saw with those faces. So the idea is that you're moving around the latent space and you're able to discover sounds that hopefully have some similarity, and because they're made up of learning what makes humans, how sound works for us, in the same way as a pig truck, gives us maybe some new ideas about how sound works. And, as you probably know, you can make these yourself, which I think is, in my mind, my favorite part about the Ensign Super Project is that this is open source GitHub. For those of you who are makers and like to tinker, please give it a shot. If not, we'll see some coming available from tons of people who are building them on their own. So I want to keep going with music, but I want to move away from audio. And I want to move now to musical scores, musical notes. Something that, think of last night with Justice driving a sequencer. And talk about basically the same idea, which is, can we learn a latent space where we can move around what's possible in a musical note, or a musical score, rather. So what you see here is some 3-part musical thing on the top and some 1-part musical thing on the bottom, and then finding in a latent space something that's in between, okay? And now I put the faces underneath this. What you're looking at now is a representation of a musical drum score where time is passing left to right. And what we're going to see is we're going to start, I'm going to play this for you. It's a little bit long, so I want to set this up. We're going to start with a drum beat, one measure of drums, and we're going to end with one measure of drums. And you're going to hear those first. You're going to hear A and B. And then you're going to hear this latent space model try to figure out how to get from A to B. And everything in between is made up by the model in exactly the same way that the faces in the middle are made up by the model. So as you're listening, basically listen for whether it makes musical sense or not, the intermediate drums. Let's give it a roll. So there you have it. Moving right along, it turns out, take a look at this command. This makes sense to some of you, maybe. We were surprised to learn after a year of doing Magenta that this is not the right way to work with musicians and artists. I know, I laughed too, but we really thought, hey, this is a great idea, guys. It's like, paste this into terminal. And they're like, what's terminal? And then you know you're in trouble, right? Okay. So we've moved quite a bit towards trying to build tools that musicians can use. This is a drum machine, actually, that you can play with online, built around TensorFlow.js. And I have a short clip of this being used. What you're going to see is all the red is from you as a musician. You can play around with it, and then the blue is generated by the model. So let's give this a roll. This one's quite a bit shorter. So this is available for you as a code pen, which allows you to play around with the HTML and the CSS and the JavaScript. And really amazing. A huge shout out to Tero Parviainen, who did this. He grabbed one of our trained Magenta models, and he used TensorFlow.js, and he hacked a bunch of code to make it work, and he put it out on Twitter, and we had no idea this was happening. And then we reached out to him. I reached out to him on Twitter. I was like, Tero, you're my hero. This is awesome. And he's like, oh, you guys care about this? I'm like, yeah, of course we care about this. This is our dream, to have people, not just us, playing with this technology. So I love it that we've gotten there. So part of what I want to talk about today, actually close with, we've cleaned up a lot of the code. In fact, Tero helped. And we're able to introduce Magenta.js, which is very tightly integrated with TensorFlow.js. And it allows you, for example, to grab a checkpointed model and set up a player and start sampling from it. So in 3 lines of code, you can set up a little drum machine or music sequencer. And we're also doing the same thing with SketchRNN, so we have the art side as well. We've seen a lot of demos driven by this, a lot of really interesting work, both by Googlers and by people from the outside. And I think it highly aligns well with what we're doing in Magenta. So to close, we're doing research in generative models. We're working to engage with musicians and artists. Very happy to see the JavaScript stuff come along, which is really seems to be the language for that. Hoping to see better tools come and heavy engagement with the open source community. If you want to learn more, please visit g.co/magenta. Also, you can follow my Twitter account. I post regular updates and try to be a connector for that. So that's what I have for you. And now I'd like to switch gears and go to robots. Very exciting, with my colleague from Google Brain, Vincent Van Ook. Thank you very much.
All right, thanks, Doug. So my name is Vincent, and I lead the Brain robotics research team, the robotics research team at Google. When you think about robots, you may think about precision and control. You may think about robots, that live in factories. They've got one very specific job to do, and they got to do it over and over again. But as you saw in the keynote earlier, more and more robots are about people. Right? They're self-driving cars that are driving in our streets, interacting with people. They essentially now live in our world, not their world. And so they really have to adapt and perceive the world around them and learn how to operate in this human-centric environment. Right? So how do we get robots to learn instead of having to program them? This is what we've been embarking on, and it turns out we can get robots to learn. It takes a lot of robots. It takes a lot of time. But we can actually improve on this if we teach robots how to behave collaboratively. So this is an example of a team of robots that are learning together how to do a very simple task, like grasping objects. Right? At the beginning, they have no idea what they're doing. They try and try and try, and sometimes they will grasp something. Every time they grasp something, we give them a reward. And over time, they get better and better at it. Of course, we use deep learning for this. We basically have a convolutional network that maps those images that the robots see of the workspace in front of them to actions and possible actions. And this collective learning of robots enables us to get to levels of performance that we haven't seen before. But it takes a lot of robots. And in fact, this is Google. We would much rather use lots of computers, if we could, instead of lots of robots. And so the question becomes, could we actually use a lot of simulated robots, virtual robots, to do this kind of task and teach those robots to perform tasks? And would it actually matter in the real world? Would what they learn in simulation actually apply to real tasks? And it turns out the key to making this work is to learn simulations that are more and more faithful to reality. So on the right here, you see what a typical simulation of a robot would look like. This is a virtual robot trying to grasp objects in simulation. What you see on the other side here may look like a real robot doing the same task, but in fact, it is completely simulated as well. We've learned a machine learning model that maps those simulated images to real images, to real-looking images that are essentially indistinguishable from what a real robot would see in the real world. And by using this kind of data in a simulated environment and training a simulated model to accomplish tasks using those images, we can actually transfer that information and make it work in the real world as well. So there's lots of things we can do with these kinds of simulated robots. This is Rainbow Dash, our favorite little pony. And what you see here is him taking his very first steps, or very first hops, I should say. He's very good for somebody who's just starting to learn how to walk. And the way we accomplish this is by having a virtual Rainbow Dash running in simulation. We train it using deep reinforcement learning to run around in the simulator, and then we can only basically download the model that we've learned in the simulation onto the real robot and actually make it work in the real world as well. There are many ways we can scale up robotics and robotic learning in this way. One of the key ingredients turns out to be learning by itself, self-supervision, self-learning. This is an example of, for example, what you see at the top here is somebody driving a car. And what we're trying to learn in this instance is the 3D structure of the world, the geometry of everything. What you see at the bottom here is a representation of how far things are from the car. Right? You probably are looking at avoiding obstacles and looking at other cars to not collide with them. And so you want to learn about the 3D geometry based on those videos. The traditional way that you would do this is by involving, for example, a 3D camera or a LiDAR or something that gives you a sense of depth. Here we're going to do none of that. We're going to simply look at the video and learn directly from the video the 3D structure of the world. And the way to do this is to look at the video and try to predict the future of this video. You can imagine that if you actually understand the 3D geometry of the world, you can do a pretty good job at predicting what's going to happen next in a video. So we're going to use that signal that tells us how well we're doing at predicting the future to learn what the 3D geometry of the world looks like. So at the end of the day, what we end up with is yet another big convolutional network that maps what you see at the top to what you see at the bottom without involving any 3D camera or anything like that. This idea of self-learning or just learning without any supervision directly from the data is really, really powerful. Another problem that we have when we're trying to teach robots how to do things is that we have to communicate to them what we want, what we care about, right? And the best way you can do that is by simply showing them what you want them to perform. So here's an example of one of my colleagues basically doing the robot dance, and a robot that is just looking at him performing those tasks and trying to imitate visually what he is doing. And what's remarkable here is that, even though the robot, for example, doesn't have legs, it tries to do this crouching motion as best it can, given the degrees of freedom that it has available. And all of this is learned entirely self-supervised. The way we go about this is that if you think about imitating somebody else, for example, somebody pouring a glass of water or a can of Coke, it all relies on you being able to look at them from a third-party view and picturing yourself doing the same thing from your point of view, what it would look like if you did the same thing yourself, right? So we collected some of this data that looks like that, where you have somebody looking at somebody else do a task, and you end up with those two videos of one taken by the person doing the task and another one taken by another person. And what we want to teach the robots is that those two things are actually the same thing. So we're going to use, again, machine learning to perform this matchup. We're going to have a machine learning model that is going to tell us, OK, this image on the left is actually of the same task as this image on the right. And once we've learned that correspondence, there are lots of things we can do with this. One of them is just imitation like this. Imagine you have somebody pouring a glass of water. The robot sees them. They try to picture themselves doing the same task and try best they can to imitate what they're doing. And so using, again, deep reinforcement learning, we can train robots to learn those kinds of activities completely based on visual observation without any programming of any kind. So I won't let that robot pour me a beer quite yet, but it's very encouraging that we can just have robots that understand essentially what the nature, what the fundamentals of the task is, regardless of whether they're pouring a liquid or they're pouring beads or whatever the glasses look like or the containers. All of that is abstracted, and the robot actually really understands deeply what the task is about. So I'm very excited about this whole perspective on teaching robots how to learn instead of having to program them. Right? At some point, I would want to be able to tell my Google Assistant, hey, OK, Google, please go fold my laundry. Right? And for that to happen, we're going to have to rebuild the science of robotics from the ground up. We're going to have to base it on understanding and machine learning and perception. And of course, we're going to have to do that at Google scale. With that, I'm going to give the stage to Debbie, who's going to talk to us about cosmology. Thank you.
Okay. Thank you. Good afternoon, everyone. My name's Debbie Bart. I'm going to be talking about something a little bit different from what you've heard so far. So I lead the Data Science Engagement Group at NERSC. Now, NERSC is the National Energy Research Scientific Computing Center. We're a supercomputing center up at Lawrence Berkeley National Lab, just over the bay from here. We are the Mission Computing Center for the Department of Energy Office of Science. And what this means is that we have something like 7,000 scientists using our supercomputers to work on some of the biggest questions in science today. And what I think is really cool as well is that I get to work with some of the most powerful computers on the planet. One of the things that we're noticing, especially in the last couple of years, is we've seen that scientists are increasingly turning to deep learning and machine learning methods to solve some of these big questions that they're working on. And we're seeing these questions showing up in our workload on our supercomputers. So I want to focus on one particular topic area. It's very close to my heart. Which is cosmology, because I'm a cosmologist by training. My background is in cosmology research, because I've always been interested in the most fundamental questions that we have in science about the nature of the universe. And perhaps one of the most basic questions you can ask about the universe is, what is it made of? And these days, we have a fairly good feel for how much dark energy there is in the universe, how much dark matter, how much regular matter there is in the universe. And there's only about 5% of regular matter, which is everything that you and I and all the stars and all the dust and all the gas and all the galaxies out there, they're made of regular matter. And that makes up a pretty tiny proportion of the contents of the universe. The thing that I find really interesting is we just don't know what the rest of it is. Dark matter, we don't know what that's made of, but we see indirectly the gravitational effect it has. Dark energy, we don't know what that is at all. That was only recently discovered about 15 years ago. And dark energy is just the name that we give to an observation, which is the accelerated expansion of the universe. And this is, I think, really exciting. The fact that there is so much that we have yet to discover means that there are tremendous possibilities for new ways for us to understand our universe. And we are building bigger and better telescopes. We're collecting data all the time, taking images and observations of the sky to get more data to help us understand this. Because we only have one universe to observe, so we need to be able to collect as much data as we can on that universe, and we need to be able to extract all the information we can from our data, from our observations. And cosmologists are increasingly turning to deep learning to extract meaning from our data, and I'm going to talk about a couple of different ways that we're doing that. But first of all, I want to kind of ground this in the background of how we actually do experiments in cosmology, because cosmology is not an experimental science in the way that many other physical sciences are, because there's not a lot we can do to experiment with the universe. We can't really do much to change the nature of space-time, although it would be fun if we could. But instead, we have to run simulations. So we run simulations in supercomputers of theoretical universes under different physical models, under different parameters that control those physical models. And that's how we experiment. We run these simulated universes, and then we compare the outputs of these simulations to our observations of the real universe around us. So when we make this comparison, we're typically using some statistical measure, some kind of reduced statistic like the power spectrum, which is illustrated in this animation here. The power spectrum is a measure of how matter is distributed throughout the universe, whether it's kind of distributed fairly evenly throughout space or whether it's clustered on small scales. And this is illustrated in the images on the top of the slide here, which are snapshots of a simulated universe run in a supercomputer. And you can see that over time, gravity is pulling matter together. So that's dark matter and regular matter. Gravity is acting upon that, collapsing the matter into these very typical cluster and filamentary type structures, whereas dark energy is expanding space itself, expanding the volume of this miniature universe. And so by looking at the distribution of matter, we can start to learn something about the nature of the matter itself, how gravity is acting on that, and what dark energy is doing. But as you can imagine, running these kinds of simulations is very computationally expensive. Even if you're only simulating a tiny universe, it still requires a tremendous amount of compute power. And we spend billions of compute hours on supercomputers around the world on these kinds of simulations, including the supercomputers that I work with. And one of the ways that we're using deep learning is to reduce the need for such expensive simulations. Similar to the previous speaker was talking about, Benson talking about in robotics, we're exploring using generative networks to produce, in this case, this example, two-dimensional maps of the universe. So these are two-dimensional maps of the mass concentration of the universe. So you can imagine the three-dimensional volume collapsed into a two-dimensional projection of the mass density in the universe as you're looking out at the sky. And we used a GAN, which is based on a fairly standard DC GAN topology, to produce new maps of these new mass maps based on simulations. So this is an augmentation. We're using this network to augment an existing simulation to produce new maps. And we see that it's doing a pretty good job. So just by looking by eye at the generated images, they look pretty similar to the real input images, the real simulated images. But as a scientist, kind of squinting at something and saying, oh yeah, that looks about right, is not good enough. What I want is to be able to quantify this, to be able to quantify how well the network is working, and quantify how like the real images our generated images are. And this is, I think, where scientific data has a real advantage compared to natural image data. Because scientific data usually, very often, has associated statistics with it. So statistics that you can use to evaluate the success of your models. So in this case, we were looking at reduced statistics that describe the patterns in the maps, like the power spectra and other measures of the topology of the maps. And we see that not only do the maps look about right, but the statistics that are contained in those maps match those from the real simulations. So we can quantify the accuracy of our network. And this is something that potentially could be useful for the wider deep learning community. Using scientific data that has these associated statistics could be of real interest, I think, to deep learning practitioners in trying to quantify how well your networks are working. So I mentioned before that this is an augmentation GAN that we've been working on so far. It can produce new maps based on a physics model that it's already seen. And we're working at scaling this up and producing physics models that the network has never seen before, so making this into a true emulator. And this will help reduce the need for these very computationally expensive simulations and allow cosmologists to explore parameter space a bit more freely. And I'd like to explore a little bit further what this network is actually learning. I saw a really interesting talk this morning here that was touching on this kind of thing, how we can use machine learning to gain insight into the nature of the data that we're working with. So in the work that I'm showing here, we were looking at which structures in our mass maps are contributing to the model, and most strongly contributing to the model, by looking at a quantity called saliency. And so if you look at the map of saliency, which is the black and white image here, you can see that the peaks in the saliency map correspond to peaks in the mass map. And so these peaks in the mass map, these are concentrations of matter, and these correspond to galaxy clusters, typically, in the real universe. And this isn't news to cosmologists. We've known for decades that galaxy clusters are a really good way of exploring cosmology. But the shapes of the features that this network have learned are not nice round Gaussian balls. They are irregular, and they're showing some structure. And this is something that's really interesting to me. And there's also indications that some of the smaller mass concentrations are showing up as important features in this network. And that's perhaps a little bit unexpected. So by taking this kind of introspection into the features that our network is learning, we can start to learn something about the data and get insight into some of the physical processes that are going on in our data, and learn what kind of structures perhaps are most sensitive to the interplay of gravity and dark energy. I think this is something that's a real strong point of deep learning, when you are allowing the network to learn features for itself rather than imposing features, doing feature engineering, or telling it any particular statistics. You can allow the network to tell you something about your data that might surprise you. So far, that was looking at two-dimensional maps. But of course, the universe is not a two-dimensional place. It's at least 4 dimensions. Perhaps many more dimensions, depending on your favorite model of string theory. But we've been looking at 3 dimensions as scaling this up another level. And the reason why 3 dimensions are interesting from us from a computational point of view, because in a 3-dimensional data volume, you're looking at 3-dimensional matrices, 3-dimensional convolutions. This is something that's computationally expensive, and it's something that can run really well on a supercomputing architecture. So a team at CMU recently demonstrated for the first time that deep learning can be used to determine the physical model of the universe from 3-dimensional simulations of the full matter distribution. So this is the full 3-dimensional matter rather than a 2-dimensional projection of the matter density. And this work showed that the network was able to make significantly better estimates of the parameters that describe the physics of the simulated universe compared to traditional methods, where you might be looking at one of these statistics like the power spectrum. And so this is a really nice example of how the network was able to learn what structures in this 3-dimensional matter volume were important, rather than just looking at statistics that we in advance thought was going to be useful. So we're working on scaling this up at the moment in collaboration with NERSC, UC Berkeley, Intel, and Cray, who are our industry partners at NERSC. We're using larger simulation volumes, even more data, and we're using TensorFlow running on thousands of CPU nodes, achieving several petaflops of performance on Cori, which is our flagship supercomputer. But perhaps the most important part of this is that we're able to predict more physical parameters with even greater accuracy by scaling up the training of this. And this is something that we're really excited about. And I think it's worth talking a little bit more in technical detail about how we achieve this performance, how we are using TensorFlow on our supercomputers to get this kind of performance and get this kind of insight into our data and into our science. Now, supercomputers are fairly specialized. We have specialized hardware to allow the tens of thousands of compute nodes we have on these supercomputers to act together as one compute machine. We want to use this machine as efficiently as possible to train our network. We have a lot of performance available to us. We want to be able to take advantage of that when we're running TensorFlow. So the approach we take is using a fully synchronous data parallel approach, where each node is training on a subset of the data. And we started off, as many people do, using gRPC for this, where each compute node is communicating with a parameter server to send their parameter updates and have that sent back and forward. But like many other people have noted, this is not a very efficient way to run at scale. We found that if we were running beyond 100 nodes or so, then we had a real communication bottleneck between the compute nodes and the parameter servers. So instead, we use MPI, which is a message passing interface, to allow our compute nodes to communicate with each other directly, so removing the need for parameter servers. This also has the advantage that it can really take advantage of our high-speed interconnect, the specialized hardware that connects our compute nodes. So we use, for gradient aggregation, for this we use specialized MPI collective all-reduce, which is designed by Cray, who are our partners with our supercomputers. And this MPI all-reduce is pretty neat. It's able to avoid imbalances in node performance, the straggler effect that some of you might run into. It's overlapping communication and compute in a way that allows very effective scaling. And we've seen that we're able to run TensorFlow on thousands of compute nodes with very little drop in efficiency. And something that I've been really excited to see here is that MPI all-reduce is coming soon in TensorFlow. And we're excited to see how this is going to work in the larger community. So the three things I'd like you to take away from this talk, the first is that cosmology has some really cool science problems and some really cool deep learning problems. The second is that scientific data is different from natural image data. And so these well-understood statistics that we often have associated with the scientific data could be of real use, I think, in the deep learning community. And the third thing is that MPI all-reduce, in our experience, is the optimal strategy for scaling TensorFlow up to multiple nodes. And we're looking forward to seeing how the rest of the community is going to work with this. So now I'll turn things back to Laurence. Thank you.
Thank you, Debbie. Great stuff, actually simulating universes. So we're running very short on time, so I just want to share, these are like just 3 great stories, but there are countless more stories out there. This is a map that I created of people who've starred TensorFlow in GitHub and who've shared their location. And we have people from the outback of Australia to the green fields of Ireland, from the North Arctic Circle in Norway, all the way down to Deception Island in Antarctica. There are countless stories being created, countless great new things being done with TensorFlow and with machine learning. We think some of those stories are yours, and if they are, please get in touch with us. We'd love to hear them and would love to share them. So with that, I just want to say thank you very much for attending today. Enjoy what's left of I/O and have a safe journey home. Thank you.